Swayam Prabha. Digital India. Educated India.
In the previous lecture, we started finite element analysis of torsional vibration. In finite element method, we started with very basic concepts like element, node, and shape function, and gradually we developed finite element formulation for one element, and we developed the mass matrix and the stiffness matrix of an element, in which what we started with the equation which we developed for the continuous system of torsional vibration of the particular shaft, and today we will be extending that particular concept for development of the system equation for using those elemental equation. And apart from that, we will see several examples how this finite element method we can able to apply for various kind of boundary conditions, especially if boundary conditions are complex. The finite element method can handle such complexity, and then we will develop some kind of equation or elemental equation for gear, because in torsional oscillation previously we have studied a geared system and also the branch system. So, some initial development of the elemental equation we will try to develop in the present lecture. So, let us see what are the things we will be covering. So, basically we will be extending the finite element method which we developed in the previous lecture, and through some examples we will be illustrating this particular method. Even we will try to develop some kind of elemental equation for geared system. So, in this basic concepts would be like elemental equation, system equation, boundary condition, how we can able to apply, and gear element. So, these are the things we will try to cover in the present lecture. So, we will start with the equation which we left in the previous lecture. So, this was the elemental equation which we developed. So, the form of the equation is mass matrix and inertia term, the acceleration term, angular acceleration, stiffness and displacement. This is the reactive torque, and this is the external torque. And these mass matrices we in the previous lecture we explained how we can able to obtain using the shape functions. So, because this is a row this is a column vector and this is a row vector. So, if we multiply it, we will get the multiplication of this two vector as a matrix. And for a representative case, let us say if we want for the elemental matrix, if we want the M12 element, that means here we need to integrate from 0 to L over the length of the element rho j n1, n2 and dz, and n1 n2 we have already obtained earlier. These are the shape function. So, n1 was 1 minus z by L and n2 was z by L integration. So, if we integrate this, we will get this particular term, that means we will get rho j L by 6. Similarly, we can able to calculate other terms by substituting the relevant shape functions, and we can able to get the mass matrix. On the same lines, we can able to obtain the stiffness elements, like if we want k to 1, this particular term. So, we need to integrate from 0 to L g j, and in this we have derivative of this shape function. So n1 with respect to z and n2 with respect to z. And if we differentiate this quantity, obviously we will get minus 1 by L, and from second term if we differentiate this with respect to z, we will get 1 by L dz, and this will give us this particular Gj by L minus term. So that is K21. Similarly, other terms we can able to obtain on the similar lines. Now till now, and these were the other terms, the reaction terms, which after substituting this we obtain them in this particular form. So this is the reaction at let us say ith node, and this is the reaction torque at the jth node, and these are the external torque. If we know how these distributed torques are varying, then we can able to put that particular variation, and we can able to integrate with respect to z to get the form of explicit form of the this kind of external torque case. Now once we obtain this elemental equation, now through one example of a cantilever shaft, we will develop a system equation, because in this particular, for illustration purpose, we have divided the shaft into simple two elements. So this is the first element and this is the second element. Both the element size is same. So if total length of this is L, so the element size L is for each of this element would be L by 2, but not necessarily we should always take the same length, but in this particular case we have taken two elements as same length. In this particular case, this property of the stiffness and the mass is distributed throughout the length, and during discretization using the finite element method, we are considering that this distribution property of the mass and stiffness both, as we have developed the elemental matrices for that particular case. And so this is one of the element, this element, and in this element we are assigning the node 1 in the left side, node 2 in the second other side, and this is a local coordinate system, and at each node we are assigning the field variable, that is angular displacement phi z1 and phi z2 corresponding to the nodes. So in finite element method, basically we will be obtaining the displacements at these two locations, and intermediate locations we will be obtaining using the shape function interpolation. And this is the second element, and this is the common node to this. So this node is 2 and this particular node is 3, and we have for this also we have local coordinate system z, and angular displacements here is phi z2 and here phi z3, because this is a common node. So we expect during assembly we should have the same displacement at this location, and compatibility of this we have already seen in the while choosing the shape function. Now once we have divided the whole system into two elements, the boundary conditions will take care of subsequently once we will get the system equation. So now let us concentrate on the element. So for element 1, if we want to obtain the equation of motion for element 1, the form of the equation will be exactly same as we have obtained earlier. So this is the mass matrix. Here for element 1 we had the node 1 and 2. So corresponding acceleration, angular acceleration terms are there, phi z 1 and 2. This is the stiffness matrix term. Here phi z 1 and phi z 2 displacements are there. Reaction torques are TR1 and TR2. This is minus and this plus, as we have seen earlier. According to the convention, it comes out like this. external torque, if it is there, they will they will be coming here at node 1 and node 2. Now, the second element, the mass matrix, because the size of the element is same, will remain same. Here there will be change. You can able to see now here angular displacement 2 is there and angular displacement 3 is there, angular acceleration. So this is the only difference, otherwise this stiffness matrix remain as same as the previous one. So here also phi z2 and phi z3 corresponding to the two angular displacement of that particular element. Now these are the reaction torque. So this we can able to write it as TR2 and this is minus TR2 and this is TR1 or TR3, because this is corresponding to the third node. This is the external torque at node 2 and node 3 of element 2. So superscript is representing the element and subscript is representing the node number. Now once we obtain elemental equation 1 and 2, we can able to combine them in as a system equation. So how we can able to assemble them? So let us see. This is our mass matrix. Now stacking up the eigenvector will be like this, because there are 3 nodes in the system. So in system equation we expect these 3 field variable will be there, plus we will be having stiffness matrix and here phi z1, phi z2, phi z3. You can remove this. So now I am putting, and in the extreme case we will be having the torques. So now I am inserting the first equation in this. So we will be having the common term, that is rho j L by 6 will be common, which will be outside, and here 1 or 2 1 1 2, this is corresponding to this. So you can able to see phi z1, phi z2, phi z1, phi z2. So they will be in the first row, first column, and in the first 2 row and column they will come. Similarly, the stiffness matrix, this is common, so this will be outside. So this will be placed in the 2 by 2 size. So where the phi z1 and phi z2 will be multiplied, they will occupy that position. Here in the torque, you can able to see here we will be having TR1 and TR2, and this minus TR2 will be added. Sorry, this will be TR2, because at present we have inserted only the first element. So now you can able to see we have inserted the first element, remaining elements are 0 at present. So if we expand this, basically we can able to get the first equation. Now I want to insert the second equation. So second equation, this particular displacements are for 2 and 3 nodes. So 2 and 3 nodes are here. So this particular 2 term of the mass matrix will come here, because this will get multiplied with the z2. So plus 2, and the 1 is multiplied by phi z3. So phi z3 in that same row, it will come here, and these 2 will come then at the lowest position at the here. So you can able to see as 2 1 2 1 is corresponding to this particular mass matrix element, corresponding to the second element. And similarly for stiffness, we will be having plus 1, this is plus 1, minus 1, minus 1, 1. So, you can able to see this particular 4 elements are corresponding to this one. Now, in the here right hand side, basically we should have equality here. So, this 2 will come here. So, we will be having here plus TR2 and sorry, this is minus TR2 this is minus TR2 and TR3. So, you can able to see that here TR2 was from element 1 and this TR2 is from element 2. They are same, so they will cancel each other at this particular node. So, this is the assembled form of the equation of element 1 and 2, and the same thing I have written here. So, this is the assembled mass matrix, this is the assembled stiffness matrix, and these are the internal torques. So, basically these are nothing but TR1 and these are TR2 and this one is TR3. These are the external torque. So, this is corresponding to the element 1 and this is corresponding to element 2. Now, once we have assembled equation, now we need to see how we can able to apply the boundary condition of the problem. In the boundary condition we had, this is the element 1, element 2, this is node 1, node 2, node 3. So, this at node 1 we have fixed end. So, their displacement and acceleration we expect to be 0 at node 1, and this at node 3 we have free end. So, it cannot take any torque. So, that means TR3 reactive torque will be 0. So, in the system equation, if we want to substitute this, we will see that this particular term will be 0, this will be 0 because this is a fixed end, and this one is, this term will be 0, and these two are equal and opposite. So, they are anyway they are cancelling to each other. So, you can able to see we could able to apply the displacement, angular displacement condition, also the torque at the node 3 equal to 0. Now, this equation we can able to this we already applied the boundary condition. So, this equation will reduce in size because some of the terms are 0. So, you can able to see this particular term is 0. So, this will get multiplied with the first row. So, whenever we try to expand it, the first row will not contribute anything, and so this particular row we can able to delete. Similarly, here this will multiply to this particular row, this will get deleted. Now, in the right hand side, in the reactions torque, if we see the second one is 0, third one is 0. Only thing is the first one is containing the reaction torque at the support, which is unknown to us. External torques will be known to us. So, because in right hand side we have one unknown. So, this particular equation which is containing additional unknown, we will eliminate from the equation. So, first row we will be eliminating in this, that means the first row we can able to delete. This equation we can able to use subsequently for obtaining the reactions at this location once we have solved the angular displacements of the system. So, we have removed the first equation, first row, first column and first row in each of these matrices, and whatever the remaining is left out, that will be 2 by 2 matrix, that we will call it as a reduced form of the equation. So, that will be basically of this form. this is the reduced form. So, these were the boundary condition which we applied in this, and in this particular case we removed the first row and first column of this. So, basically you can able to see reduced form is this 4 is coming here, 1 and 2 is coming here. Similarly, this 1 plus 1 2 is coming here. So, this is the reduced form of the equation, and these are the external torque which are known. So, now this equation is ready for solution, because now you can able to see this is having standard form as m phi double dot z plus stiffness phi z is equal to some external torque. So, this is a standard form of the equation for multi-degree of freedom system. So, that can be solved either for forced vibration or free vibration. In this particular case, we divided the shaft in 2 elements, but if we want to have more accuracy, we need to have more number of elements in the system. So, I am just explaining if we have 3 elements, how the system equation will change. So, for that particular case, let us say we have this and we have 3 elements. So, we will be having node 1, 2, 3, 4 nodes will be there. So, we will be having 4 angular displacements, and the assembled equation, because we need to first write the elemental equation for first element, second element and third element, and then we need to combine them. So, we already done up to the second one, but if third is also there, then we will be having, can able to see earlier it was 3 by 3 size, but now 4 nodes are there. So, we will be having 4 angular displacement, and mass matrix will be again, can able to see the form will be similar to the previous one. In this contribution from the second element and the first element both are there. Similarly, here contribution of this second and third element is there, and this is the from the third element. So, basically this is coming from 2 plus 2, and similarly this is coming from 2 plus 2, and in this stiffness matrix also this is from one element and the second element, and here also from second element and one element. So, this is just extension of the previous assembled equation for 3 nodes or 3 elements, and here in torque we will be having 2 common nodes, that is node 2 and 3. So, we will be having contribution from element 1 and 2, they will cancel each other during the assembly because they are reaction torque, and similarly at the node 3 they should cancel each other because this is a reaction torque. So, when we are assembling these two parts, two elements, obviously the reaction torque should cancel each other, and these are the external torque. So, this is just an illustration that if we have more number of elements, how the equation would change in the assembled form, but we will continue with the same 2 element for the free vibration analysis of the this particular cantilever shaft. We developed the reduced form of the elemental system equation with the help of 2 element. We will continue with the 2 element, and we will try to solve the free vibration. That means, we will try to obtain the natural frequency of the system using the finite element method. So, for that our reduced form was 2 by 2 matrix earlier. So, we are assuming the solution of that in this form, in which this is the amplitude part, which could be complex, and this is the harmonic part in which the frequency is there. And because that particular equation, the previous equation was containing derivative with respect to the time. So, if we derivate this, we will get this one. So, basically you can able to see that in previous equation in the reduced form, if we substitute these solutions, so we can able to we are substituting this solution in the previous mass matrix. In this we had and then the stiffness matrix, and time dependent term, there is E j omega nft is outside, and this is for free vibration. So the external torques we are keeping at 0. Now you can able to see back this equation. This is the mass matrix, this is the stiffness matrix, this is 0 because free vibration. Now if we substitute those equations, those matrices here and here, and because this two vector are common, so we will be having the form of the equation as minus this m plus k, and this will be outside, and because this time dependent term will not be there. So now you can able to see this is a homogeneous equation, and if we equate if we put this equal to 0, there is no motion of the system, so this cannot be 0. So the determinant of this to be 0, and that is that particular term in which we are combined the mass matrix and the stiffness matrix multiplied by this particular natural frequency square term. So if we equate this, we will get a polynomial of this form in the quadratic in omega nf square, and if we solve this quadratic equation, we will get the natural frequency 1 and 2. So these are the natural frequency of the system using finite element method. Earlier we obtained the closed form solution for this particular case, and we expect that closed form solutions are exact values, and from that these are the natural frequency, and if we compare, the first natural frequency was 1.57 and this factor, and from finite element method we are getting 1.6114, so they are close. Second natural frequency was 4.71, exact one, but with finite element method we are getting slightly higher, and so the second natural frequency is not that much accurate here, but if we take more number of elements, we expect the finite element results will be giving better results, closer to the closed form solutions. The same problem we are solving here in the form of eigenvalue problem. So the previous equation, which was which we had as omega nf square m plus k, and this is equal to 0. So I am multiplying both sides by k inverse of the matrix and dividing by the natural frequency square. So if I do it, you can able to see that k inverse into m is a is k inverse into m, and lambda is 1 by omega n square because I have divided throughout by omega nf square. So this lambda is 1 by omega nf square, and because there is no other term, so this is identity matrix, and A matrix is the inverse of k into m. We can able to do the multiplication of this, we will get this. Now if we solve the eigenvalue problem of this matrix, we will get two roots like this, and these two roots are nothing but inverse of the natural frequency square, because here eigenvalues are defined like this. So you can able to see that if we invert this and take a square root, we will get the same natural frequency values which we obtained earlier. So directly from eigenvalue problem we can able to obtain the natural frequency, and corresponding to that particular A matrix, this is the eigenvector. With software like MATLAB, directly we can able to get the this eigenvector, and this eigenvector is representing how those two particular node, the second and third, are getting displacement, because in the previous equation we had two field variable 2 and 3. So, they are belonging to that, and we already know that at node 1 we have 0 displacement. So, this vector can be extended like this to represent the how at node 1, 2 and 3 the displacements are taking place, okay, and we can able to draw the mode shape. This will be more clear if we take more number of element. So, the size of the eigenvector will be more, and we can able to see the shape of the mode shape more clearly. Similarly, when we are taking more number of elements, we will be getting more number of natural frequency, and we expect the natural frequency which will be the lowest one or the lower ones will be better as compared to the higher ones. We will take up another example. Now, we will see a slightly more complex boundary condition, and we will see how the finite element method can tackle more complex boundary condition. Such boundary conditions, if we want to apply using the continuous system approach, it will be very difficult, if not impossible, but it will be very difficult to apply and get the closed form solution. So, now let us see another example in which we have let us see the first problem. So, fixed end, this is a shaft having distributed property, this is a rigid disc at the free end, and also there is a spring attached at the free end of the disc. In the previous case we had only cantilever shaft, but now disc is there. Apart from that, we have one a spring, a torsional spring attached to the free system, and for this we have various property like the shaft property is given, length of the shaft is given, torsional stiffness of the spring is given, diameter of the shaft, the property, the density of the shaft, because we are considering the distributed property of the shaft, and modulus of rigidity is also given. So, we need to obtain torsional natural frequency of the system using the finite element method. So, these are the various property which of the shaft and the spring which are given, and other property which we can able to calculate using this are second moment of area, that is polar second moment of area. Element in this particular case, we will be dividing this particular shaft in two element only. So, the element size of that will be half, and these are the other mass property and the stiffness property. Now, let us see how we will be discretizing this particular system. So, as I mentioned, I will be discretizing this particular shaft in two elements, and this will be the third element. This particular disc, either we can able to take up along with the element 2 or along with the element 3. So, for this case we will take this particular disc along with the spring the element 3. So, now I am drawing the 3 elements separately. So, this is the first element having node 1 and 2. This is the second element having node 2 and 3. This particular disc I am carrying along with the third element. So, let us say this is the third element, this is node 3 and this is node 4. So, you can able to see this particular system I have divided into 3 elements. The first element is this, second element is this, and third element is this. So, total 4 nodes are there, and now we can able to obtain elemental equation for each of them. So, first step would be that. So, this is the same the division of the element, and in this itself we will see that how we can able to develop the elemental equation for this. For that, this is the free body diagram. We will see later this how this free body diagram can be useful for development of the elemental equation for this. So, let us write the elemental equation for first element, which is simple. This is the first element having node 1 and 2. So, correspondingly this will be the mass matrix. These terms we already calculated earlier. Here these field variable is corresponding to node 1 and 2. This is the stiffness matrix. Here again the corresponding to node 1 and 2. These are the reaction torque at node 1 and 2. So, they have this particular form. Similarly, for second element, which is identical to the first one in shape and size, but only the node number are different. So, you can able to see here remaining things are same, only thing is this particular field variable is having subscript 2 and 3, and here 2 and 3 corresponding to the 2 and 3 nodes of the element 2. And similarly, here we have the reaction torque TR2 and TR3. So, we have developed the elemental equation for element 1 and 2. Now, we will see for third element how we can able to develop the element. So, now we are concentrating on this to develop the elemental equation for this. So, for this I have drawn the free body diagram of the these two parts, disk separately and the spring separately. So, disk is having, let us say, this particular angular displacement is positive in this direction. So, the reactive torque will act opposite to that in this direction, and this will also act in the opposite direction. So, this reactive torque is from the shaft. You can see this particular disc is not only attached to the spring, but it is attached to the shaft also. So, this reactive torque is coming from the shaft, and this reactive torque is coming from the spring, and this spring is having relative twist of theta 3 minus theta 4, because two field variables are there. So, phi z3 minus phi z4 is the relative twist into the torsional stiffness will give us the reaction torque from the spring. Now, this is the free body diagram of the disc, and the same reactive torque will act here, but direction will be opposite here, and this will be opposite. Here also the same reactive torque will act, because there is no other forces here. So, the torque here and torque here, they should be same. Now, let us take the free body diagram of the this particular disc. So, we have reactive torque from the shaft, from the spring. This should be equal to the inertia of the disc. Similarly, from this this reactive torque of the spring is nothing but the is coming from the relative twist of the shaft. So, there is no inertia. So, this will be 0. So, now we can able to see that these two equations we can able to combine in this form. So, the first equation is here. If we expand the first equation, we will get this. We have substituted the value of the IP and T also, KT also. So, the first equation is this equation. If we expand the second equation, that is this equation. So, basically we assemble these two equations, and this is the elemental equation for the third element. And now we have obtained elemental equation for 1, 2 and 3 element. Now, we can able to assemble them, and assembly obviously because we have 4 nodes. So, this vector will be having subscript 1, 2, 3, 4. So, this is the assembled mass matrix. So, you can able to see this is coming from element 1, and this is coming from element 2, and this term is coming from the element 3, and there is no term here because in the element 3 only one mass term was there. Similarly, in the stiffness, this first 4 are corresponding to element 1, and these are corresponding to element 2, and remaining 4 are from element 3. And you can able to see at intermediate node 2 and 3, reaction torque will cancel each other. This is the reaction torque at fixed end, and this is at the other extreme end of the spring. And this is the simplified form of the previous equation. We have added those coefficients, and so this is the simplified form of the previous equation. Now we can able to apply the boundary condition. Boundary condition at node 1 is that displacements are 0, and at node 4 also the other end of the spring the displacements are 0. So that means we can able to put this equal to 0, this equal to 0, this equal to 0, this equal to 0. So these are 0. So we can able to see that once we have these 0, so they will multiply with the first row, so they will not contribute anything, and the first and the fourth row are containing unknown, so they can be eliminated and they can be used subsequently to obtain the reaction torque, but at present first and the fourth row can also be eliminated because in the right hand side they are containing unknown. Similarly, this fourth, these 4 will get multiplied with the fourth row. You can see this will multiply with the fourth row. So we need to eliminate them. Here we have 0, I think. So you can able to see that we have only 2 by 2 matrix, that is this one for mass matrix, and 2 by 2 matrix for stiffness matrix, and right hand side is 0. So if we write them separately, this is the reduced form of the equation. You can able to see this was between after deleting rows and column, this is the mass matrix, this is the stiffness matrix, they are this, and right hand side is 0. Now for free vibration we can able to convert this particular term as minus m omega square and angular displacement 3. So and this will be common. So as we did earlier, we need to have the determinant of this term to be 0 for non-trivial solution, and this will give us a polynomial in terms of omega and f square, and that will be having this form. And if we solve this polynomial, we will get 2 natural frequency of the system. So you can able to see that using finite element method we could able to get the 2 natural frequency. Closed form solution of this is not easy, but with finite element method the same elemental equation was helpful in obtaining the natural frequency of the system quickly. Now we will take up another example in which we will be taking a more number of element, and we will try to study the convergence of the solution. So we will see that how many element number we should choose for a particular application. With this exercise it will be more clear. That means we expect generally when we are taking more and more element, the solution should converge toward the exact value. And this particular study is also called convergence study. So let us take the case of a simple continuous shaft, and this particular shaft is having, so we have a continuous shaft of 3 meter length, diameter is given, and this is having distributed property. This particular shaft is supported freely, and we have we need to obtain up to the fifth natural frequency, the natural frequency as well as the mode shape. So you can able to see that we will be taking 5 element, 10 element, 20 element, 50 element, 100 element and even 500 element, just to see how the results changes with the number of element, and we will be comparing the natural frequency with the closed form analytical solution. Basically, in this particular case, the boundary condition is free boundary condition, and for that we have the closed form solution available. So these are the various property of the shaft. So for illustration purpose, I have divided the shaft in 5 element, and because of that we have 6 nodes, 1, 2, 3, 4, 5, 6. These are the various property because the elements are same. So we will be getting the element length, various geometrical property, mass property and stiffness property from the given data we can able to obtain. Now we can able to write the elemental equation for any representative element, because all element is same. So we can able to see that j can take from 1 to 5 value. So that means we need to write this equation 5 times with different nodal displacement vector, because we are divided into 5 element. And let us say for the third element, this particular element will take phi z3 and phi z4, and here we will be having torque 3 and 4. These are the reaction torque. We are considering free vibration, so there is no external torque. So these 5 equations, as such elemental equation, we can able to combine, and this is the assembled equation. And this you can able to see all the node, 6 nodes were there. So we will be having field variable corresponding to all 6 nodes. And here the assembly, as we discussed here, will be having the first 2 by 2 as for first element, and remaining will be having second element, third element, fourth element and fifth element. And the form of this equation is of this. So this is the mass matrix, inertia, this is stiffness, and this is the reaction torque. For this, because this free condition, both the ends are free, so it will be having boundary condition as torque at 1 and 6 as 0. Here intermediate torques at common nodes will be 0, but because of free end, this torque will also be 0. So this is the application of the boundary condition. So because all vector here are 0, so none of the rows and columns we need to eliminate them. And this particular, for free vibration, this acceleration term we can able to write like this. This we already seen it, and we can able to formulate the eigenvalue problem as we did earlier. So here we have inverted the mass matrix instead of the K matrix. So eigenvalue will be this one. So whatever the eigenvalue will be getting, square root of that will be the natural frequency. So for D matrix, which is inverse of mass matrix into K, we will be solving the eigenvalue problem, and square root of that eigenvector will give these natural frequencies, and that is for the 5 element. So these are entered here. So you can able to see this for 5 element. These are the natural frequencies. Then if we want to take 10 element, we will get these natural frequency. We will get more natural frequency, but I am summarizing only the first 6. One of the natural frequency is 0. So you can able to see that for 10 element, there is hardly any very small change in the first natural frequency, but higher frequencies are getting changed more. This is not changing. So this for 10 element, but as we increase the number of element to 20, 50, 100, you will see that most of the value are changing very little. That means we can able to see up to 20 element, hardly 0.1 change is there. Here there is some change here. So if 100 is good enough, I think, for the convergence, but just for checking up to 500, if we take the element, you will see that the values are quite stable, and these are the values corresponding to the closed form solution. So, you can able to see for 500 number of elements, we are getting the exactly same as the closed form solution. So, this is the convergence study. As we increase the number of element, if there is not much change in the natural frequency, that means we can able to assume that we have achieved the convergence. And these are the mode shapes. These are the mode shapes which we can able to plot it. So, for first mode, this is the rigid body mode. Second mode is this one. Third mode is this one. Fourth one is this one. So, you can able to see these are coming directly from the eigenvector, and eigenvector will give us the displacement at the node position. In between, we can able to interpret using the shape function. So, these are the shape functions which directly we are plotting from the eigenvector. Today's lecture, we have seen the how the elemental equation which we developed in the previous lecture can be used for obtaining the assembled equation or this equation for the system equation. And once we have the system equation, we can able to apply the boundary condition of the problem at that stage, and then we can able to obtain the natural frequency of the system and also the mode shape. And through various examples, we have seen how powerful is this finite element method, and even the not only the complex boundary condition, also based on the number of elements. If we increase the number of elements, even we can able to get the natural frequency quite close to the closed form solution. And in the subsequent class, we will explore the finite element method for the gear element and the branch system, which we could not able to cover in this particular lecture.